to TikTok, Real Talk. We're still working on the name. John Jeno, welcome back. Thank you very much, sir.
Glad to be here.
Yeah, same here. All right, so one of the things I love about doing these things live, first off, is you're getting a legitimate and real authentic conversation, and we get to experience little things like real life issues. And I love that. So we have two wonderful guests for you today. While we work on getting Mike back, we're going to go ahead and introduce Mr. Kevin Jackson. Donnie, why don't you give us a little round of applause for Mr. Kevin Jackson. And John, why don't you do us a favor and let's introduce Kevin to the world and let's let everybody know who Kevin is, and we'll give Kevin an opportunity to do so.
Well, crying out loud, I met Kevin way back on the 23.5 meter days for due diligence out of UC Davis, I believe it was. Kevin's the aero guy when it comes to blade designs and the manufacturing processes. Got a good eagle eye on quality systems, what works and what doesn't work, and has just a wealth of experience. He's one of, I believe it was Mike put it yesterday, one of the dinosaurs. And being unattached, running on his own, he's free to speak his mind, which is great for us here. This is what we're trying to get people to do. Let's get over to Kevin.
Yep, absolutely. Now, Kevin, why don't you give us a little bit about your background? And as we get into this conversation today, which I'm excited about, our pre-call yesterday, it got some good debate. And I'm looking forward to getting Mike back on, who is currently jumping over from Safari to Chrome, all the wonderful technical things. But I want to give you an opportunity here. Introduce yourself to our group and give us a little bit of your background and what qualifies you to get into this conversation today for the others that don't know who Kevin Jackson is.
Sure. Yeah, my background is I got started when I was in my 20s at UC Davis in Northern California. And at that time, there was a lot of wind energy happening in California. It was the leader globally, really. By the end of the 80s, we had about 70%, I think, of all the global capacity that had been installed. So I happened to be in the right place at the right time and kind of grew up with the industry, spent a lot of time in the field, starting in my 20s, and a lot down in Southern California, in Tehachapi and Palm Springs area, where we have both of those areas have a lot of wind. And then gradually, as the industry expanded, moved elsewhere in the United States, and now we really do projects all over North America in my group, in wind crews.
All right.
Awesome. And it looks like we got Mike. Mike, you're back. Mike, can you hear us all right?
I can hear you. Can you hear me without an echo?
Here we go.
Yes. All right. We did it, you guys.
What about?
I think we have a show. All right. I'm going to take a minute here. Sorry, but I'm going to let the little audience out there understand what we just accomplished was pretty damn amazing. We got one guy out in the woods on a landline. And this is not a system designed for that. And this young man here, who's done a great job at producing these shows, says, Dad, I can troubleshoot a lot of things. I cannot troubleshoot a landline. I don't know what to do, and I don't know how to help us on this, but we figured it out, and this has just been amazing. I am so glad this worked out, because if you are watching this program right now, you are about to get into a really great conversation, and we are going to bring up some topics and questions that I hope really create some challenging arenas for you to question and understand, are we truly in the right place right now as an industry in regards to standardization, in regards to holding accountability? And we like to talk about the responsibility versus accountability, but we're going to get into this. And this is primarily as we continue our discussion in talking about blades, understanding all of the aspects when we talk about the cradle to grave. But more importantly, today it's focusing on the standardization when it comes to these lightning arresters. So you don't know Mike. I want you to get an opportunity to know Mike. Mike, why don't you give us a quick introduction of who you are and your experience in this area, and just introduce yourself to our audience, and then we're going to get into this.
Sure. I'm one of the old timers in the industry. Started out in 1977, if you can believe that. So 45 years in the industry. Started out in the design side of blades in wood epoxy, and then over the years did research work as the materials changed, got into fiberglass, got into carbon fiber, worked the aerodynamics side of it, the structure side, the fatigue side, and lately lighting is becoming ever more important. And so I think that's why I'm on this call. Anyway, that's the quick look at it. Any further questions or clarifications needed, I can do that later.
I just got to ask Mike, what's that shirt?
Yeah, can you see it?
I just had to ask that. That's cool.
I'm a veteran of my first 10 years, 5 of them in Apollo, all the Apollo landings, and then 5 more in Space Shuttle. It was
that's just cool stuff. Okay.
Totally,
Yes, it is.
It was totally fun.
I bet. That's just giving you guys a little bit of an understanding of the kind of caliber of folks that we have on here today. So I'm excited about this, and I hope you guys are too. So here it is. Let's get into it. All right. So John and I, we've been discussing a lot of this stuff, and there's a couple things that I want to get into. But first, let's just ease into this, John. Let's roll into this a little bit in terms of before we really start hitting hard. What is it that we are seeing today that it seems to be very similar to what we've seen in the last 5, 10, 15, maybe even 20 years?
As 20 plus years ago, as we started making sub-megawatt and megawatt size blades in the States, we are seeing the same problems in the field that we saw back then. We're seeing various construction methods for lightning systems inside the blades that work kind of sort of most of the time, work if they're built correctly, every single detail, every single time. And this is human beings putting these together. That's not happening. And we see the results on the negative side out in the field. But the questions of it didn't work too well. Well, I shouldn't say it didn't work too well. There were issues on smaller turbines and rotors. And here we are growing into multi-megawatt size. And we'll be asking Kevin and Mike about what does that mean to us as we go larger. We are seeing other things on top of the problems we still have left over from 25 years ago. Why are we still there? Why are we still in that situation? And then we can address the future problems to come as well. So is the standard appropriate for where we are today before we jump forward?
So we started talking about certifications and what does certifications mean? Okay. And so today we have a process of protocol that we're holding manufacturers accountable to. And so from your guys' perspectives, Kevin, and I'll put this over to you, what have you seen in terms of over the last few years on how we are holding the certifications for manufacturers, and like, are they staying in line with what's happening in terms of the changes of size or magnitude of the blades in comparison to our standards and our quality standards and the certifications that the blades need to be at?
That's a big question.
Yeah, I mean, I think the standards represent sort of minimums in a way. I mean, they're something everybody agrees upon. And it depends exactly which standard we're talking about. There's some international standards, the IEC standard, which is kind of the typical lightning standard. But then there's also Germanischer Lloyd, which is now merged with Det-Norsk Veritas DNV. But GL used to have its own standards that they would apply, and DNV now has merged those. So there's some DNV standards, and they're part of. They're kind of separate in a way. They refer back to the electrotechnical standards, and so I think in general they're constantly being updated. but it's kind of one leg in a stool. I always think of there's sort of three legs. One is that you design it well using good standards, and then you have to build it properly is the second leg. And then the third leg is you have to install it and maintain it properly. And it really takes all three of those legs to prevent failures in the field and to get good operations. And sometimes it's one or the other. It's sometimes related to things that are in the standards or the way that usually it's the way that the standards are implemented, probably.
Okay, so Kevin, back in the day, the IEC first standard came out in 2010. Is that correct?
Yeah, the history goes back into the late 90s, and they had what was called, it was part of the IEC, they had TC, Technical Commission, I think, 88. And it was a group that got together, and they published a document in 1999, I think, called TC 88. It was more of a guidance document. Some parts of that still persist in the current standard, in the appendices.
So back
but
then,
the first real standard is 2010.
Okay, I recall back in around 2004, 2003, that one of my competitors at the time came over for a whatever chat and made the statement that they had a proprietary lightning protection system, and that was they had nothing conductive in the blade, and therefore lightning wasn't going to hit it. And one of my grunt engineers asked at the time, pointed out, he didn't ask, he pointed out that his kid's birthday party, they rub balloons in their hair and stick them to the wall. And that got a blank look from my competitor at that point, but it did stop the conversation. So at that time, prior to 2010, it was not there was not a standard applied to the industry. There were recommendations. So when you certified a blade, was it certified to a lightning standard back then?
Yeah, that's correct. It basically, there's this technical commission TC 88 document that floated around. It's just recommendations that got updated to a report, TR level, and that was in 2005, I think, and then in 2010 was the edition 1. So the first real agreed upon standard out of IEC. Now there were requirements through Germanischer Lloyd. They used to call it the Blue Book requirements. So there's various things that might talk about lightning that were in other standards, but really until 2010 there was no guidance document that said you have to follow this in order to be under a standard.
And so a certified blade may or may not have been following those guidances at that point, and you can still get insurance on it.
Right, and the difference between like the TC level, it's sort of early. There's no shall, and that's the big thing in the standard. It defines things that you shall do.
Yes.
In order to be compliant with the standard.
Okay. All right. So let's jump up to the 2018. The revised standard is out, and there will be a link to a summary of that someplace on Rigo's page here at the end of this. And glancing at that, there's a lot in there that's been updated. I don't know a lot of what I'm looking at. I was really happy to see that HSC, the employee technicians HSC, is in there. Part of that is during a thunderstorm, where can people be located, up tower or inside the tower? That's called out. Where should they not be? Obviously, the exterior of the nacelle example, but it's actually part of the standard now. I was happy to see that. Has the standard been updated to where we can be of some use for our larger turbines? And let's just hit that really quick. Compared to the old 750 size machines and today's machine, you and I had discussed some time back about what that means in terms of lightning risk. And so where are we at today with today's larger turbines compared to back then in terms of getting hit?
Yeah, I think that's one of the big issues with the larger turbines is they're much taller and the rotors are much larger. So the capture area, the collection area for a 125, it's on the order of a square kilometer for each turbine. And so in kind of some parts of the Midwest that are on the worst side, you're probably looking at 6-8 strikes per turbine per year kind of thing. It's down to maybe just 3 or 4 in other parts. So it's significant. Every turbine is going to be hit multiple times per season, when the lightning season comes through.
And there was another something I stumbled on yesterday, a couple of DNV's transcript of their conversation, and that'll be linked on the site as well. And they're talking about turbines that are taller tend to have more upstrike than downstrikes, and where the upstrike is DC based versus the high frequency of the downstrikes. And from what I call, again, on earlier conversations, the detection system, or I guess it's a system, is it Visalia? How do you pronounce that?
Yeah, typically the National Lightning Detection Network is a company called Visalia. They provide the data commercially, and they've been looking at how many of the radio detection network. It's a group of antennas that are national in scale, and they triangulate based on when a lightning strike happens, it creates an electromagnetic discharge that you can measure in the radio frequency. And then they triangulate to where that is. We get the data as an error ellipse. So we have a probability that it's within that ellipse. And then we can calculate based on that which turbines have a probability of being hit. But that system may not detect everything, right? So there are some parts of the strike that might not be detected. So we've been tracking that, and I know in general the system's pretty good, but there may be some things that come through that are new, and then just the sheer scale of what we're putting out there in terms of the size of the turbines means new behavior can happen that we just don't understand yet, and that's certainly possible.
There's other. The term of "we don't understand yet," from what I saw from the transcripts yesterday, there's a lot of that going on as things are getting larger, not just in the frequency of getting hit due to the size, but also in the materials and the constructions being used. We're seeing things that we didn't see before on the smaller blades. And I'm wondering, when these are tested, lightning test systems, I've seen, Google it up to find images online where it's the tip section of the blade, sitting in a lab someplace with a lightning bolt coming out of the tip. And it doesn't look like it reflects the entire system. I understand in the standard, there are requirements for the grounding side and bearings. Is that correct?
The typical testing that gets done is on tip sections, and so it's usually just a portion of the tip. And with the larger blades, it's some tens of meters perhaps that goes in, but you don't get the whole system from the tip to the root generally tested. It's just too big to fit into the lab space.
And we're seeing some things in the field that might indicate that's not sufficient to not be testing the middle third of the blade, for example. And Mike, we had talked about that, I believe yesterday as well, that the construction method is coming into play, especially with these higher strikes. We've got low, medium, or small, medium, and large lightning strikes, and now there's a new term being thrown out there for something larger than that. Can you discuss in general? I don't, no specifics. What we're seeing happen out there with our larger constructions in the middle of the blade versus the tip in the root.
Sure. What Kevin, of course, is talking about is a reality in the test labs, and unfortunately, not all the activity that we're seeing is just confined out there to the tip regions. So if you've got what's called a flashover, is a typical problem that's emerging now as being more important. It's when an electrical discharge is occurring within the blade, between the main down conductor and some piece of conductive structure in the case of carbon fiber blades. Or it might be that you're even further inward, even in the vicinity of the root, and you would have a discharge that would leap from a piece of conductive structure into one of the attachment studs. So all of that part, which is a lot of the blade, it's not in the test lab. And another thing that goes on that we're becoming increasingly sensitive to is the idea that at radio frequency, the energy is moving, well, in air, it's about a foot per nanosecond, right? That's speed of light. And so these things move very rapidly, and they can rattle around within the structure. You can have reflections and electromagnetic couplings and things like that. Those things are important in the inner part of the blade that you just asked about, but they're not tested because of the limitation of the facilities. So that's kind of my quick take.
Can they be modeled? If we can't test it, how are we designing these things? Just blindly? I'm afraid so.
Well, not quite. I mean, one of the things that you try to do in a case like this is you make a model, and then you use what you can get from the lab to see if your model is giving you the same kind of results that you're measuring to the extent that you can in the laboratory. And then you take that and extend it to the parts that you can't measure, extrapolate to different sizes or extrapolate to different current levels, that sort of thing. But right now, in fact, I'd say the kind of level of the industry is that they're using the lab data as much as anything to tune the models and then trying to squeeze out of the models the information they need. But going back to what you were discussing earlier and Kevin was discussing earlier, we're pushing into size realms where it's not necessarily clear that we're even doing all the right modeling or doing it the right way to address what's going on at those scales.
And we are now finding materials acting in ways they did not act before. Is that because of size and the power of these strikes?
Indeed so. When we had quite small blades, the distance over which a current discharge was going to go was limited by the length of the blade. So as the blade gets longer and longer, the antenna, if you would, which is the down conductor, right? That antenna is becoming larger and larger and larger. So its ability to couple energy out into the outer world is growing as a function of size.
So, okay. So as a real world hands-on experience as a comparison, I'm trying to put this in some terms that people who aren't familiar with radio.
Yeah, I'm just thinking like bigger blade.
So long ago, I had about 30 meters of twisted pair wiring for a sensor system, 4 to 20 milliamp stuff, and I'm frying the input card to the computer. Couldn't figure out what was going on, and then it dawned on us: there's a guy right next to us on a parallel path with a 6-inch steel pipe, and he's welding on it. And that was it. My sense line turned into an antenna, and I actually had arcs on the cards in the PC from what he was doing 3 feet away.
Yeah, well, you're basically hitting on it in a very practical way. So here we've got this huge, long down conductor, right? And we've got these huge, long carbon fiber spar caps. Oh, goody. What is that? That's kind of like a linear transformer. Same sort of thing you're talking about. You blast a chunk of current down the one, especially if it's got high frequency content, it reaches across the gap, induces voltages and currents into the parallel element, and then they run around doing their thing, uh, even though they're not physically connected to the down conductor.
So would this bring us into the other conversation, John, where we talk about unicarbon versus the bias carbon? We talked, yeah. So we talked a little bit about this here the other day offline, where we were discussing the new material in the production aspect of how these layering of these materials together in order to create the size that are needed, in the end, are creating a conductive material and doing the opposite, correct?
I'll kick that over to Mike and Kevin. What have we learned about
gonna,
carbon fibers in their orientations? Does it matter?
Well, I'd love to talk about that, but Kevin is the one who's been digging up some really interesting stuff on this recently, so I'm going to defer to him to do this.
Yeah, we've got some reports. There's been a lot of work done on the research, especially because carbon fiber is getting into aircraft, and so aircraft also have a lot of lightning-related issues, and so what we're finding from multiple sources in lab tests is that the impedance, which is sort of the resistance to in an AC world, it's kind of the equivalent. That the impedance follows inductive characteristics, as if it was an inductor on the unidirectional materials. And the plus or minus 45 materials look like capacitors in a circuit. And so when you hit it with a lightning strike, you get a lot of frequency content because it's a fairly jagged event, and that creates a lot of frequencies. And under different that frequency content, you'll get different responses out of the electrical circuits that when they're inductive versus capacitive, and that can induce different electrical potentials between them because they're one is lagging behind the other one, and so you'll get these voltage differentials, and then potentially there'll be a spark that will cross an arc that'll go from one layer to another potentially. So yeah, so it's interesting where somebody might be doing a structural design wouldn't think about what are the electrical ramifications of this, and then the sheer volume of the material now is getting to the scale where they're fairly large capacitors, they're fairly large inductors. They have mass, and ability to store charge because of the scale of it. So I think that's the part that's changing. There is some physics here that's different. We're reaching farther up and having bigger collection areas, so it's happening more frequently. I think that the frequency of it is the thing that the industry needs to grapple with. This is not an unexpected event. This is going to happen. Like I say, every blade a couple times a year is likely, has a probability of being hit. So it's one of those things that you just, as an industry, have to cope with it, and our systems need to work. And that's really what the standards are about, is that they basically say you should take a lightning strike up to 200 kiloamps, and there can be only so much damage that you can leave the turbine running until the next scheduled maintenance. So the idea of the standard is you're going to get hit a bunch over the years, and you should get maybe some small dings, but they should be such that you don't have to bring the turbine offline.
So if I'm an owner operator and I get hit with 180, I should be able to, and damage is incurred, I should be able to go to whether it's the manufacturer or have it covered by insurance. And where? where I'm getting to is the term force majeure comes in here at this point on, are lightning strikes covered by insurance policies or not?
Yeah, I think, if it's a standard, if it's a blade that's under the standard, so you're applying the current standard, then the standard anticipates that you're going to get strikes up to 200 kiloamps. And then the requirements in the standard, the language is pretty clear that, the blade, the LPS system shall protect the blade, such that if there is damage, it's not significant enough to prevent the turbine from normal operation. Okay. So basically strikes under 200 kiloamps, you should be able to accept and not be damaged in any significant way structurally.
Okay, we'll come back to that in a second. But there's a question I see. Stefan's asking, Kevin, are you saying the carbon fiber may create a path of lesser resistance than the conductor?
It's electrically connected into the down conductor. Sometimes there's connections directly from the carbon to the down conductor. I mean, that's common, but it's also connected electrically through the electromagnetic radiation that's given off by the down conductor. So there's different ways they can communicate, some of which are not by wires. The standard will allow you to connect them in. It will allow you to leave them unconnected. But you have to model it properly. And so there's a bunch of issues related to how you go about through the certification. You have to show the certifying authority that you've thought through your lightning system and that it functions as it's supposed to. But then, as we say, some of the testing, it may not measure the whole system. So there may be a hole in the system or in the analysis that we're doing of those final, manufactured systems, because they're really not looked at from top to bottom in the lab typically.
Okay, so I want to place an order for new turbines. The latest, the greatest, the largest. Is the new 2018 standard sufficient? What I'm hearing is probably not, because we're stumbling onto things physics-wise that we just didn't see with the smaller blades. The sizes are there, the giant capacitors are coming into play, the material's acting differently, or at least it's acting the same, but its size now comes to the point where it matters for us. How do I defend myself? I want to buy turbines. I want a contract that says everything's covered. I doubt that's economically possible. So how do we pressure the manufacturers to step up the game as far as design goes?
I think one of the things is to acknowledge the issue right up front. So the National Lightning Detection data is available historically. So as part of citing, there's no reason that we shouldn't have these numbers ahead of time and basically discuss that as part of site suitability, that, look, we expect, let's just say it's 6 strikes a year per turbine, so two strikes per blade per year. And how do we should expect that's going to happen, and we shouldn't be surprised by it. And over the life of 20 years, it's going to grow to 100 or so strikes. It's not in any way something we should be surprised about. It's like all kinds of other severe conditions. It's a normal operating condition to be hit by lightning in the Midwest. I mean, it's just totally normal.
I saw a comment.
It's not weird.
I saw a comment yesterday claiming that the term force majeure is a safety net. It's a crutch. Allowing that to be in the contract gets the manufacturers off the hook. Oh, lightning's a strike. We can't handle it. Force majeure. It's like getting hit by a tornado, I suppose. That takes away the pressure to improve the design.
And if I might comment for just a second, if we're talking a 400 kiloamp strike, it's not required that the system do that. We've seen pictures of 400 KA strikes, right? Stuff melts. It's not like you can't tell that this was one of the strikes that was really, really big, but there aren't very many of those, okay? What Kevin is talking about, the vast majority of those are within the limit that the system is supposed to handle. What insurance should be doing in the very rare cases, relatively low numbers, where it was this monster strike. Okay, yeah, that truly is outside the tail end. It's a tail end of the distribution. Let insurance pay for that. But they shouldn't and can't keep their economic model intact if they're paying for strikes that are 100 kiloamps or 50 kiloamps or maybe 30 kiloamps. That won't work from the standpoint of the economic model that insurance companies have to live by.
So I'm gonna come in here with a little bit of from an ignorant point of view. Okay, so I'm coming from, I've been in the industry 15 years. I've worked operations. I know enough, but I am not in any level educated in this field. So from a common thought perspective, I'm thinking, but aren't they supposed to be able to handle lightning strikes? Like, if you're going to build something that brings giant lightning attracting type of material, they're just giant lightning antennas in the sky, and the bigger they get, you're going to get more lightning strikes. That's just what I'm thinking, is the bigger they get, the more strikes you're going to get. My question is this a technology failure in terms of being able to put in the right type of technology that will pass that lightning strike through? Or is this a manufacturing error? Or is this just somebody not really taking the time to recognize that we're far behind where we should be?
Yeah, well, I might point out there's some pretty big carbon fiber aircraft flying around, and they are not allowed to fall out of the sky because they got hit by lightning. Okay. No,
that is a really good point. This is one of the things I think we were talking about yesterday, and what I wanted to kind of get into is, it seems that if we were in a industry where lives mattered, like airlines, like automobile and others, it seems like the standards are held at a much tighter, standard, and you don't get the opportunity to push out designs or new model upgrades without truly understanding that we have lowered the risk to almost nothing. Okay, Johnny. Yep. So here we go. We're talking about, it comes down to the money, right? But now there's a lot of companies out there that offer equipment, right? They offer upgrades into the blades to help with lightning. You made a comment earlier, Mike. You said they're supposed to be able to manage. What does the standard say they're supposed to be able to handle in terms of a lightning strike?
Well, I think Kevin can probably go into the details of
Kevin,
standard
can
better
you?
than I can, but the basics are. Go ahead, Kev.
Yeah, it's 200 kiloamps is the typical current. There's a number of things that the standard outlines, how much energy, the total energy discharge and total charge and things like that. But the typical thing is the amperage, and that's 200 kiloamps. And, as you say, Mike has indicated, we'll do the analysis. We get the lightning data from the National Lightning Detection Network through VISLA. And so we'll get thousands of strikes. Often we'll get a 2-year period when we're looking at projects. And then we can sort through what the size of them was, because that's part of the data set is how many kiloamps. And what we find is very, vanishingly small is above 200 kiloamps. There's not much. And that's what the standard anticipated. That's why they set that limit, because they figured 200 kiloamps is virtually all of the lightning strikes that are out there. And so I don't think that's a flaw in the standard, and I don't think there's a flaw in the standard. The standard requires that you take a lightning hit under 200, and sure, you can peel a little bit of fiberglass around the puck. You might, have a little bit of damage, but it's nothing that's going to take the turbine out of service until its next scheduled maintenance. So I think, interpreting the standards and actually, having them have force that's the part where it's really commercial. None of these are required by any laws. These are all commercial agreements that people decide to do. And so not all manufacturers certify their turbines in the same way. Some of them don't certify turbines anything more than just beyond the design part of it. They don't actually do a full type certification under the way that it's anticipated. Many European companies do, but often American companies have not.
Okay.
But it's commercial, so it gets interpreted often through business negotiations.
All right, we've got another Kevin question posed for you up here. Can you discuss what polarity does to a strike within the LPL1? Context: a manufacturer is trying to make all damage force majeure, even if measured strike is under the LPL1 due to polarity. So I think this is what we were talking about earlier with the larger rotors. According to one study from DNV, is having more up strikes on larger rotors compared to the past. And that is a heavy amount of DC. I'm assuming that's what due to polarity means, is direction.
I haven't spent a lot of time looking at the directionality. Rick Santos has done more work on that than I have, and he's not with us today, unfortunately. But so I'm not sure I can respond directly to that question.
I understand there's a mess of high-speed photography going on recently, where and going forward, specifically for lightning strikes, and they're able to start now quantifying how much is going down, how much is going up, and then look at damages from that point. How did the system perform under these different conditions? So that'll be interesting stuff. But that's just fairly recent. We'll see.
Okay, well, I'm a physics guy, right? And so I'm going to make some broad comments on this topic, and that is, if I push a bunch of current they call it DC, but let's just say it has a small amount of high frequency, a relatively small amount of high frequency content, right? So that's going to minimize the kinds of electrodynamic effects that we were talking about that can induce flashovers or induce currents in parallel elements. That kind of strike isn't going to cause those kinds of damages because it lacks precisely the characteristics, i.e. the high frequencies, needed to do so. That can't be a way out in terms of explaining, it shouldn't have happened. If you're talking about just the total Coulombic delivery, right? How many electrons float? A long DC strike can do a lot of that, but what's that going to do? It's going to heat up conductive elements and melt stuff. If you're melting stuff, okay, that's a relevant question to raise. If you're not melting stuff, if you're doing flashovers and the like, it doesn't fit the physics.
All right.
So go ahead, John.
Yeah, Rigo, I was just going to ask, the paper I had sent in about the changes from 2010, 2018. It's just a brief overview of what changed in the spec. There we go. So is that going to be available?
This one here? Yeah, so we can drop the link, but if you guys want to kind of help me through what this document is and explain it to our audience, I think that would be great.
This is just a high-level overview of what the 2018 does above and beyond the 2010.
Okay, so we will make that available. We'll go ahead and put that into our comment section. And when we update this, we're going to go ahead and put that out there for everybody as well. So one of the things I want to let everyone know too, for those of you guys that are on, we appreciate your patience. LinkedIn was not behaving properly with us. We've had a good number of viewers coming on and watching live with us. Thank you guys very, very much. We will be rebroadcasting this right after to LinkedIn again, since LinkedIn did not want to share it on all the channels. But we're happy that you guys followed us over onto our YouTube channel. And that's why we always have the YouTube channel as a backup. If it wasn't one thing, it's another. But I just want to thank everybody for being here. We are getting ready to kind of wrap this up. And so I want to give you guys the opportunity to share some aspects to this, because I think it's an important discussion. I think that there is a lot of touchy areas in regards to what's happening, but it seems very much to me that we've been doing this now nearly 20 years with large blades. They're getting larger, and it doesn't seem that we're getting better at solving the problem.
And that's the disappointing part.
Yeah, I mean, we figured out a lot of things. Like we you know, when you look at drivetrain, we started off with a non-synthetic. We learned very quickly that you cannot run a non-synthetic lubricant with these types of pieces of equipment. We've come to find out quite a bit in regards to drivetrain and keeping them running longer. We've done that with a lot of different areas of the technology in a wind turbine. We've learned that we can produce more by making them bigger. Shocker. But it seems like when it comes to blades, which are by far the most expensive asset for a owner operator, why are they getting damaged more? Why are we seeming to have more issues? And I don't think that this is good for anyone in the long run, especially when we are representing ourselves in an industry that's supposed to be caring about the future of our planet, and we're creating products to produce renewable energy, yet we're having a lot of failures with something that already has a whole nother problem in regards to recycling. So, I mean, there's a lot, I think, that goes there. So, like, are we doing the right thing? Are we really holding ourselves accountable to bringing better technology out to really care for what we all care about? I know we are all passionate about what we do. It's a lot of what drives us, but it just feels that a lot of times this needs to come down really to an owner operator to want more, want better, and honestly be willing to pay for it. But, you know, that's not for me to say, right? But Kevin, I'd like to give you an opportunity to share some final words, final thoughts with all the research and stuff that you're doing. And Mike, will come to you next. And then John, you and I will close up.
Yeah, I think one of the things that I would say is know the hazard ahead of time. So it's not that hard to look at the lightning maps, and it's not that hard to get accurate data. We can make estimates of the lightning hazard on any given position during the planning stages. So it seems it's not that expensive to do. It seems like it should be on the table up front. We expect every turbine over 20 years to have this many lightning strikes, and basically talk about it ahead of time. So I think that's one of the things. And have the conversation, how many blades do we expect to lose over those 20 years due to lightning? I think the answer is you don't expect to lose many, if any. I don't know of projects that have spare blades on site for lightning specifically. And so if you have blades that are knocked out due to structural problems caused by lightning, that's not anticipated by the code. So I don't see that as the code failing to do its job. It seems like it's more on the enforcement side, which comes through, basically in this case, it's business negotiations. There's no legal requirement to follow the code. The legal requirements basically end at the tower. The tower goes through a county structural engineer, but then the machine that sits on the tower is not really looked at by code authorities locally. So it's really business negotiations, and it's the buyers and the operators.
Okay.
Thank you. Yeah, I'm trying, like, I want to, you left that was good, Kevin, but now I'm like, now I want to get into that a little bit, and we're out of time. Mike, I want to bring it over to you, sir.
Yeah, and I'll just be very quick here and say that we recognize that it's really, really important if you're going to have a good product that you have manufacturing sitting at the same table as design. You can't design stuff that can't be manufactured. You can't make manufacturing changes that violate fundamental design requirements. Now, what it looks like is that you better have an electrodynamicist sitting at the table too, along with your aerodynamicist and your guy who understands fatigue and all that kind of stuff. And since, I had to do all that stuff when I first started, there just wasn't those other disciplines, but we got to put all the right people in that room with those disciplines, and they all have to be there at once, and they have to talk to one another. And like I say, we're going to have somebody who really does understand electrodynamics in the room. That's it.
I love it. I love it. Listen, thank you both gentlemen for being here. Also, do us a favor, if our audience wants to find out more about what you guys are doing right now in the industry, how can they find you?
Are we going to provide the information? I mean, Windproof. We've got email addresses. Give them our email addresses.
All right. Well, we'll make sure to post it, and any websites or anything as well. And we want to thank our sponsor, Thread, for being a part of this and putting this in, out there for you guys. Thread, an autonomous inspection services. They're the leader in enterprise scale autonomous data collection for delivering precise inspection insights. So we're very happy to be partnered with Thread right now and what they're doing in the industry, making huge changes. So thank you very much, Thread, for sponsoring this opportunity for Mr. John Jeno and I to bring this stuff out to you and have wonderful guests like Kevin and Mike both. Your guys' history and experience in this area is very impressive, and I am very grateful that you guys were willing to share the things you have been able to. By all means, if you have anything else that you would like to put out, we can drop it in later, let us know, and we'll let our listeners know where they can find it. I think you guys probably have way more to share than we can do in an hour, and I would like to be able to get deeper into this discussion. But again, for everyone too, that gave us the patience getting through our technical difficulties this morning, we appreciate it. We will get this rebroadcasted out to LinkedIn right away so that those of you who missed it will get a chance to get it. And if you guys have any other questions, let us know. John, any final words from you before we let everybody go?
No, let's wrap this up.
All right, sounds good.
We need to get better.
Awesome. You guys, thank you so much for being here. We appreciate it, and we will see you next month on our next